If electric charges confuse you, don't worry. In the next few minutes, everything
All
will
right,
make
let's
sense.
dive into the invisible forces that are, well, secretly powering pretty much everything around us. Electric charges and fields. We're going to peel back the curtain on the physics behind, a tiny spark, all the way to the tech that basically runs our modern lives. You know what I'm talking about, right? It all starts with something we've all felt. That little zap you get from a doorknob, or when your hair just decides to stand on end. It feels kind of like magic, but nope, it's pure physics. So what is really going on in that split second? Okay, so that little shock, it's more than just a surprise, it's a clue. It actually points to this really fundamental mystery in physics. How can things attract or repel each other across totally empty space? I mean, without ever even touching? So, check out this simple experiment. You've got two charged glass rods, and you can see they're clearly pushing each other away. But then, you bring a charged plastic rod near one of them, and bam, they pull together. This is not random. There is definitely a hidden rule at play here, some invisible force that's calling the shots. So, to crack this mystery, we've got to find the culprit. And that culprit, it turns out, is a super fundamental property of matter called electric charge. Now, this is the crucial part. Electric charge isn't something an object gets. It's part of what an object is, It's a basic built-in property of the particles that make up everything, just like mass. And this property is the source of that whole invisible force we were just looking at. And what's really interesting is that this property comes in two distinct flavors. It was actually Benjamin Franklin who first suggested calling them positive and negative. A really simple naming system, right? But it perfectly captures their opposite nature. And just like that, we've solved our first mystery. Those two glass rods, they both had the same type of charge, so of course they pushed each other away. But the glass and the plastic rods had opposite charges, so they pulled together. It's the one simple rule you've got to remember. Like charges repel and unlike charges attract. All right, so we know what charge is. Now let's dig into the strict set of rules that it always plays by. Okay, there are three big ones to remember. First up, charge is conserved. That just means you can't create it or destroy it, you can only move it from one place to another. Second, it's additive. This is super simple. If you have, say, a +2 charge and a -5 charge in one system, the total charge is just -3. Easy. And third, it's quantized. This one sounds complicated, but it just means charge comes in these tiny discrete packets. A good way to think about it is like money, right? You can have 1 cent or 2 cents, but you can't have half a cent. Well, charge is the same way. You can have one fundamental unit of charge or two, but you're never going to find 1.5. Now, how easily these little charges can move around really depends on the material they're in. So in things we call conductors, like metals or even our bodies, charges can pretty much flow freely. But in insulators, think glass, plastic, wood, those charges are locked down tight and can't really go anywhere. And trust me, this difference is absolutely key. So that leads to a really cool question. If insulators lock charge in place and conductors let it run wild, could we, use that to our advantage? Could we actually charge something without even touching it? Okay, let's see how this works. We're going to start with two metal spheres. They're conductors, obviously, and they're touching each other. Right now, they're both electrically neutral. That just means they have no overall charge. Okay, now for step 2. We bring a positively charged rod nearby, but, and this is important, we don't let it touch. Since those spheres are conductors, all the free-moving negative charges inside them are going to get pulled towards that positive rod. They all rush over to the sphere that's closer. Well, that leaves the other sphere, the one farther away, with a buildup of positive charges. So you see, we've separated the charges. Now, here's the really clever part. While that rod is still there, holding all those charges in their separate corners, we just pull the spheres apart. And just like that, the negative charges are stranded on the left sphere, and all the positive ones are trapped on the right. And for the final step, we just take the rod away. Its job is done. The trapped charges, now free to move around their own sphere, just spread out evenly. And there you have it. We've made two oppositely charged objects, and we never touch them with the rod. This whole cool process, it's called charging by induction. Okay, so we've seen that this force exists. We know it's real. But how strong is it? Is there a way we can actually measure it or even predict it? Well, yes, we absolutely can, and we have Coulomb's law to thank for that. Now, this is the law that governs the electric force. I know it might sound a little dense at first, but the core idea behind it is actually incredibly elegant. Let's just break it down into simple terms. All Coulomb's law is really saying is two things. First, the more charge you have, the stronger the force. Simple enough, right? But the second part, this is a really deep insight into how the universe is put together. The force gets weaker with the square of the distance. So, if you double the distance between two charges, the force between them drops to just a quarter of what it was. This whole inverse square thing, it's like a fingerprint for the fundamental forces of nature. We even see it in gravity. But wait a second. Coulomb's law describes a force that somehow acts across empty space. And that's a pretty strange idea when you think about it. It leaves us with one last, really big question we need to figure out. I mean, how does one charge know that another charge is even there? There's nothing connecting them. It's just empty space. So how on earth is that force being transmitted from one to the other? The answer, it turns out, is something called the electric field. See, the idea is that a charge doesn't actually pull on another charge directly. No. Instead, it changes the space around itself. It creates this invisible field of influence. And that field is what exerts a force on any other charge that happens to wander into it. So how do we even picture this invisible field? Well, physicists came up with a great tool, field lines. And the rule is super simple. The lines always radiate outwards, away from positive charges, and they always point inwards, towards negative charges. They basically draw you a map of which way a positive charge would get pushed if you dropped it in there. And this is where it all just comes together so beautifully. When you have more than one charge, their individual fields just combine. You can see it right here with a positive and a negative charge interacting. Look how the field lines flow so gracefully from the positive charge right over to the negative one. They're literally drawing the invisible pathways of the force connecting them. So there it is, this whole invisible world of charges, forces, and fields. It's the bedrock of pretty much all of our modern technology. But think about it. Everything we've talked about so far has been static, just sitting still, which raises one last really exciting question. What happens when these charges and their invisible fields start to move?
If this helped you, support your learning, like, subscribe, and stay consistent with physics.